Welcome back. This is going to be a real short lesson on total internal reflection. And really what it is just refraction. But it enters into a realm of kind of indeterminacy. So let's check that out. Light passes from a slower medium to a faster medium. The ray is bent away from the normal. Now, how far away from the normal can you bend? There's going to be some incident angle where the refracted angle gets to 90 degrees. Well, then what happens? What takes place? So let's check this out. So here we put a light bulb in a swimming pool. How's that? So we shine a flashlight, say, down, and it hits the surface from the slower medium to the faster medium, and the refracted ray has got a larger angle. Now, if we go somewhere farther down, a larger angle, a larger incident angle, all right, that ray is going to bend more. It's going to be more bent than this one. So it's going to bend more away from the normal. Then eventually you arrive at what's called the critical angle, where the incident angle is theta critical, and that's the point at which the ray bends to 90 degrees. And it's kind of like, I guess I'm going to travel along the surface of the water. But does that really happen very effectively? What's going on there? Well, it is a place where a definite transition occurs. The refracted angle is 90, and that's called the critical angle. And here's how we find it. We find it using Snell's law, just like before. Ni sine of theta critical. So the index of refraction in the incident times the incident angle, which in this case is the critical angle, is equal to the stuff on the other side, which is the refractive index, times the sine of the refracted angle. But the refracted angle, of course, is 90 degrees. So let's solve for sine of theta critical. It is nr sine of theta r over ni. But since this angle is 90 degrees, you know what this value is. What's sine of 90 degrees? That's right. It's 1. So nr sine of 90 over ni, which is simply nr over ni. The index, the ratio of the indices, refracted over incident. That's how to find, obviously, the critical angle is just the inverse sine of that ratio. There it is. Sine of theta critical, nr over ni. Okay, now at this point, what happens is, and it's not going to refract so much, slightly back down. It doesn't do that. At this point, the transition is that it suddenly acts as though it's a reflection, and it obeys the law of reflection. In fact, it's called total internal reflection, or TIR. So up to that point, it acts like normal refraction. And then when it hits that point, the next thing that happens is it just bounces, essentially bounces off the surface, off the interface here. So that this angle, this angle, the incident angle and the refracted angle are actually the same thing. Okay, so that is total internal reflection, and it's an extension of regular refraction. It's going to have a significant role in phenomena such as rainbows, which we'll investigate very shortly. And you can use this idea to solve for problems where you have total internal reflection.